Okay. Sorry, I still don't get used to it. So then I was supposed to give a lecture on the Conformal block, but I decided to talk about something called non-invertible symmetry. I think nowadays it's functional, like kind of like a functional topic in a research field, and I think it's a good opportunity to learn some kind of like a close to the research topic, and I think it's a good time to do the review Ising CFT and so on. So today's content is not written in any lecture note, but it's there's a professor at MIT gave a very nice lecture, so I followed his lectures on non-invertible symmetry in the Ising CFT. So that's so last time we talked about the 2D Glasgow Ising model. I think it's a good place. So it's not written. I mean, there is something. His lecture note is also available. It's called "What's Done Cannot Be Undone" or something like that. To the 1D quantum Ising model. And then, so what we did is essentially we have a spin 1 and then J to L, the L side or M side, I don't care the note. Notation is just come from the Schuhenschau's lecture note today. And then at each side you have a qubit, Hj. So Kali H is the Hilbert space, is the qubit. A qubit, two-dimensional Hilbert space. So the total Hilbert space is the J equal to 1 to L. So the dimension of total Hilbert space is 2 to L. That's so here you have a spin up and spin down states at each side, and then you have the L side. So the total Hilbert space is the 2 to L. So what is the symmetry of this system? So one is the Z2 symmetry. Literally just flip the sign of either. We just map to the 0 to 1, 1 to 0 for each side. Well, I mean 0 is spin up and down, and 1 is spin up. More precisely, either is equal to product of xj. J is equal to 1 to. So here, intentionally, I changed the notation to the sigma x. It used to be something like this one. Polymetrics is sigma x, but now I use capital X to show this sigma polymetrics. So 0, 1, 1, 0. So that's polymetrics of the x direction. Of course, it's spin up goes to spin down, or spin down goes to spin up. So you at each side you swap the spin from opposite spin, and if you product all the operator or each side, you get this sign flips. So maybe this is it's not sign flip, spin flip symmetry. Okay. So, and oh, sorry, maybe I should write down Hamiltonian first. Sorry, Hamiltonian number 2. Okay, Hamiltonian of this system. So this how to say, solid H, and this Kali H is a Hilbert space, solid H is a Hamiltonian, and then minus G, sum of X, J, J is equal to 1 to L, minus G inverse, sum of ZJ, ZJ plus 1, J is equal to 1 to L. So that's the Hamiltonian we looked at the last time. So last time it used to be K here and the K prime. It used to be, and this it used to be sigma G J, sigma G J. I changed the notation to that. I mean, just follow the. Anyway, so you understand why I don't use this sigma like instead of capital X. So that was the Hamiltonian of quantizing model. Okay. Instead of G, I used K and K prime last lecture, but I just changed the notation. Okay, so it's clear that the Hamiltonian is the invariant under the spin flip symmetry, and also it's from there it's clear the translation. Lattice translation of lattice side. So namely, so T operator xj, T inverse is equal to xj plus 1, TZ, J, T inverse is equal to Z, J plus 1. So clearly, so this Hamiltonian is invariant under this translation, lattice translation. Because I mean, it's just so cool. And of course, it's so these are the symmetry of the system of the the system, and then so this is G, and when G equals to 1, you have Ising CFT, and here you have a disordered, and this is ordered phase, and then after G equals to 0, Z equals to 0, what we have is the ground state degeneracy is either 0, 0, and 1, 1, 1, like this. Okay, at G equals 0, so there's a ground state degeneracy. Ground state degeneracy. So that's either all spin up or spin down. So that's the case. And here, this Z2 symmetry is unbroken. Z2 unbroken. Because I mean, it's disordered, so spin up and spin down is even if you flip the spin, it doesn't matter. Otherwise, but here is broken. Z2 is broken, spontaneously broken. Because once you pick the vacuum of this one as a vacuum ground state here, I mean, so it's Z2 is broken. So therefore, in the effective field theory, the potential here is something like this one, or whereas the potential here is something like this. So this is lambda integral effective field theory. If you use this one. So once you pick vacuum here, the Z2 symmetry is broken. Okay. So that's a spontaneous broken of the Z2 symmetry. Okay, so that's and then we know that G equal to 1, something special happened. At the G equal to 1, I think CFT will show up, and then there is so-called Kramer's Vanier duality. Kramer's Vanier duality, which. So last time we learned that the xj is mapped to zj plus 1, and then zj plus 1 is mapped to xj. Okay. So that's the Kramer's Vanier duality we looked at last time. Let's recall what we did last time. So the last time what we did is that so we define a mu A is the last time notation is something like this one. Product of sigma A, sigma I of x, I for minus L over 2, and I is equal to A. Okay, so that's the notation, and then mu x A is the product of the power matrix sigma A plus 1. And that was a last time notation. And then in terms of this mu operator, Hamiltonian can be written is something like a G product of mu A, C is and A plus 1. Okay, so A is 1 to L, and the G inverse sum of mu A, and then x, and A runs for 1 to R. So it's not Halley Hamiltonian, so it's a solid Hamiltonian. It's a Hamiltonian. It can be written like this. So that's what we learned last time. I mean, it used to be something like this one. Sigma J C minus G inverse sum of J is equal to 1 to L sigma C J sigma C J plus 1. That was the original one, but if you use this one, mu notation, this sort of notation, you can rewrite this one. So you just swap the role of this quadratic term and the linear term and so on. You will swap the law by just exchanging G and G inverse. Okay. That's what we learned. Essentially, this mu will do the following mu of C A, and it's all spin out. Oh, okay. So my notation, okay, maybe 1 is something like from there 0 and 1, and here we have the A here and then A plus 1. That's essentially, this will give you like a kind of solidum is solitonic object. So spin 0 to 1. So it's 1 to 0 to 1 at the position of A is something like there's a kink there. So that's why it's kind of solitonic object. Okay, so that's what we learned. And here, this can be understood Kramer's 1 and empty. Essentially, we have a symmetry like this. Especially when you said G equal to 1, I mean, you cannot distinguish this term and this term, right? G equal to 1, this term and this term. So you cannot distinguish high temperature phase and low temperature G equal to 1. So both Hamiltonian is the equivalent. Okay. So therefore, we expect this kind of thing. Okay, so that's what we learned last time. Okay. Fine. And then question is there any like operator? So the A and T can be understood as the action on an operator like this one. Can we construct such an operator that induces Kramer's 1 and duality? So that's a question one can ask. Question. Can we construct an operator for this Kramer's 1 transformation? Okay. So one question one can ask. So naive guess. Okay, naive guess. If you do a naive guess, so there exists a unitary operator. So unitary operator, naive guess. such that the U xj, so it's very similar to xj, just goes to xj plus 1. That will give you translation, lattice translation. So now your guess is, can we have such an operator to realize this one, to realize this transformation? Okay. Then if you have this, if you assume this one, I mean, and Ada is like, Ada is just a spin flip operator, and this one is something like a product of j is equal to 1 to L xj, your inverse, right? And then if you apply this one into here, this will give you product of j is equal to 1 to L Cj plus 1. Okay? Cj and Cj plus 1. Okay? I mean, this j square is equal to 1 because I mean it's just a power matrix, right? It's just a 1 minus 1, 0. And if you square it, you get the identity operator. Okay? So now, and it's just adjacent operator, and then the multiply on the from 1 to L. So this means equal to 1. Okay? It's identity operator. You have two copy of Zj. Okay? So that's something strange, right? Already. So this means that the Ada is equal to 1. Okay? If you just conjugate U inverse U and U inverse Ada equal to 1, which is not true over there. Okay? Which is not true. Ada is not identity operator. Okay? So therefore, so now your guess is not correct. Now your guess, so this is not correct. Okay? Now you guess. There's something wrong in this. There's something wrong in this operation. Okay? What's wrong is that this is the assumption. This is wrong. So this Kramer's finite derivative cannot be transformation cannot be done by integral transformation. There is no so this if it is unitary, there's the inverse, unitary inverse, but that's not true. Okay. So that's the reason why you have this mountain. Okay. So to circumvent this contradiction, what we need to do is that something you have to break some assumption. Okay. So it's a bit ad hoc. So we consider the following transformation: d is equal to square root 2 d to d minus 2 pi I L over 8, and the product of j is equal to 1 to L minus 1, 1 plus I xj divided by square root 2, 1 plus I Cj plus 1 divided by square root. Okay, and 1 plus I xl over square root 2, 1 plus Ada over 2. That's the operator we consider. The operator we consider. That's a D operator. It's a bit out of hoc, but so here x and z do not commute. So therefore, this product is just from the order is something like this. Order is multiplication is always from left to right, like this way. So this product is really what is it called? I forgot the name. Sequential quantum. Let me check. Yeah, sequential quantum circuit. So this part, it's something not the translation of symmetric. So here, 1 to L minus 1 side, you have this piece, and in addition to 1 plus Ix times 1 plus I times D times D. So this one. But at L side, we don't have this piece. At L side, you only have this piece. Okay. So that's somewhat not a translation important. And here I call it this one is U cross 1. U cross 1. U cross 1. Okay. And then this is projection. This is projection. So it just keep only track of the state that is even under this Z2. For instance, if you look at ground state, you have a 2 state in here, right? 2 state in here. From there, so only even state is something like this one. Divided by 2. This is eta even. This is eta even. On the other hand, you have this state divided by 2. This is eta odd. You can easily say if you act on eta, this 0, 0, 0 becomes 1, 1, 1, right? So the 1, 1 becomes 0, 0, 0. Okay? So therefore you have a negative sign, right? Therefore it's odd. But on the other hand, here it's even. Okay? So this 1 plus eta is projection so that the it only pick the even operator, even state, sorry. Even state. Of course, this is eta squared is equal to 1. You usually check that the 1 plus eta over 2 squared is equal to 1 plus eta over 2. So that's the projection. The property of projection operator. So why do we consider this kind of operator? So if you use this property, one can show that the U cross 1 xj, U cross 1 inverse is equal to the following Cj. It behaves almost what we want. J inverse where J is equal to not equal to L. But here you have a eta times ZL Z1. J is equal to L. Okay. So there is some extra factor. So this is equal to product of xj, as I mentioned over there. Product of xj. Okay. Because of the something strange here, you will have an extra piece eta here. Okay. So therefore, this U has an inverse. On the other hand, it doesn't give us the desired property for cross 1 transformation. However, this D, okay, so this D does not have an inverse. The important thing is D doesn't have an inverse. Does not. It's non-invertible. Because it's involved projection. So once you project, this state is projected out. If you project it out, you cannot come back. Okay? So therefore, the D doesn't have an inverse. On the other hand, we have this property, D xj. So this is it's good exercise to do. D xj. Okay, so this is a property. So it has this kind of property. This is exactly what we want here. Sorry, J plus 1. Sorry, J plus 1. The important thing is that we cannot inverse D. So therefore, we cannot write down. We cannot write down like this way. We cannot write down like this way. There is no D inverse. Therefore, the best you can do is that this transformation. Okay, this transformation. Okay, so this cannot be done. This cannot be done. There. Okay. So at g equal to one, since it's not translational symmetry, right? So this UKW is not translational symmetric. So therefore, UKW do not commute with Hamiltonian. Do not commute with Hamiltonian. On the other hand, D commute with Hamiltonian. Okay. So therefore, D commute with Hamiltonian is D is a symmetry of this system. Okay. Symmetry of this system. Okay. And moreover, this UKW do not commute with you commute with translation UKW. On the other hand, D commute with translation. Okay. So this property only holds for any J. Any J. Any J. That's the so therefore, D is non-invertible, but it's a symmetry of the system. So therefore, this D is called non-invertible symmetry. Symmetry. If you look at if you search the whatever archive every day. Almost every day there is some paper which is called non-invertible symmetry of blah 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 and so on. So it's a very very passionate topic. This was introduced like 2020, I don't remember, something like that. The last past years, past 5 years, it was intensely studied for the community. But this is the simplest example of this non-invertible symmetry. You can see in the Ising model. Okay, so what is this? So summary of the symmetry in Ising CFT or Ising model. Lattice Ising model is that the A square is equal to 1 and T to the L is equal to 1. Okay? Since we have a translation, so T is a translational symmetry, this is T. So if you do the L times of translation, you should go back to the original. T to the L is equal to 1. And A to T is, should commute with T A. Okay, and then we can show that so A to D is equal to D A equal to D, and then D T inverse, D square is equal to 1 plus A over translation. So this is the property of D actually, and then also you have D T inverse is equal to T inverse D is equal to D diagonal. So these are actually symmetry of the algebra symmetry in the Ising model. And I'm going to show this property from now by using the mapping to this parametric model. This model. So these are we will show. Any question at this moment? Okay.
this operator has variable also.
What do you mean?
This operator has variable also.
You mean D admits the interpretation of the physical observable? Is that what you mean? Is that a question? I mean, it can be realized operator. So that's a definition. So it's operating in the system, but it's a symmetry of the system. It's related to, because I mean, of course it's related to, because it's a symmetry. If there is a symmetry, there is a conservation. But here, what's important is the discrete. Okay, so Z2 and Kramer's finite duality is also Z2. It's not Z2. Sorry, D square is equal to this one. So it's not the usual symmetry. So that's why it's called non-invertible symmetry. And it's discrete. And the important thing is discrete. So you cannot simply apply Nether theorem. Okay. So Nether theorem is given a continuous symmetry. There is a conserved current. But here, it's not that case. Okay. So let's derive this one. To derive this one, you map to the Ising. It's equal to Majorana fermion. Majorana fermion. This is a question mark actually. So last time we mapped to the, I changed the notation again. So we consider Majorana chain. So you just consider Conformal algebra. The last time I used psi to show the notation. Okay, I can use psi L, and then psi L, and psi L prime is equal to 2 times del L prime. So that's the we considered last time. Okay, and Hamiltonian is given by so this can be realized by psi 2L is equal to sigma whatever. Yeah. But so now I use parametrics. K is equal to 1 to L minus 1, L minus 1, and then sigma L y, and then psi 2L plus 1 is equal to K to 1, L minus 1, or maybe minus 1, or whichever is okay. Sigma K X sigma Z. So that's what we learned. Last time I used Z and X. I mean Z and X and Z and Y and so on. But the notation doesn't matter. It's just a notational problem. That's what we did, and then you just consider Conformal algebra. Okay, we consider Conformal algebra, and then Hamiltonian of this system can be written as the following: I sigma psi L psi L plus 1 L plus minus I psi 1 dot psi 2 L. Okay, L runs for 1, 2. The L minus 1. Okay, so let's start. Here I just a bit impose some boundary condition. So the difference from last time is just impose the boundary condition here. The last time I only consider plus sign, and then everything become periodic, but I introduce some boundary condition. And I call it this boundary condition, depending on boundary condition, I call it H plus or H minus. Okay. And H plus is corresponding to periodic boundary condition. In the fermionic term, it's called Ramon boundary condition. H minus is the anti-periodic. It's the Levy-Schwartz boundary condition in the fermionic language. Okay. Fine. So we consider the fermionic. So L is equal to 1, L is equal to 2, and so on. And L is equal to 2L now. Not 2L instead of L, capital L. Okay, 2L. Because I mean, because of this Crufel algebra, so as you can easily see, so that it's 2 psi will create a 1 qubit. Okay, 2 psi will create a 1 qubit. So therefore, so yeah, as you can easily see, so when here L runs from here L runs from 1 to L, right? And then 2 psi will create a 2 qubit, as you can easily see at each side. So therefore, still dimension of Hilbert space is equal to 2 to L. Okay? 2 to L. And the Hilbert space depending on the Hamiltonian, so therefore equal to plus or minus. It's a Cayley H. Any question at this moment? So if you consider this Hamiltonian, in fact, in continuum limit, as you can easily see, I mean, here. Continuum limit, you get the so-called free parameter, or real parameter. I mean, Majorana, so this Majorana means real. So this Majorana real. Real free parameter. Anyway, so reality condition is imposed. And then continuous limit. Continuum limit of this discrete system is equal to free Majorana parameter. So Lagrange is something like this one. Psi L. Okay. Chi L. Oh, sorry. So this L and R is just a left moving and right moving. Okay, so do not confuse with this one. It's just from the complex. So and then this depends on T and X. It's a continuous limit, T and X. T and X. Okay. So what is the lattice symmetry? So what is the lattice symmetry? Symmetry is the what is the called minus 1 to F. Minus 1. It just count the fermionic numbers. Okay, so therefore minus 1 to F is chi L, psi L, and then minus 1 to F, you get the minus 1 psi L. So therefore, minus 1 to the F can be defined as I to the L psi 1 dot psi L 2L. That's the definition of the minus 1 to the f. Okay. So as you can easily see, I mean, even if you swap, you just multiply minus sign in it's everything quadratic inside here, Hamiltonian. So therefore, minus 1 to the f commute with h. Okay. So therefore, it's symmetry of the system. So you can easily see that even if you multiply minus sign in each side, you get a minus times minus is plus. So therefore, h commutes with it's a symmetry of the system. So now the symmetry is translation. That is translation. Translation. Okay, so t plus psi l, t plus inverse is equal to psi l plus 1. Okay, so that's a lattice transformation for the periodic boundary condition. On the other hand, for lattice translation of the anti-periodic boundary condition is a bit more special because of anti-periodicity, and you need to impose the following condition when L is not equal to 2L or psi 1 minus sign. Okay. It's important to put the minus sign. L is equal to 2. Okay. That's anti-periodic translation. So the T minus and T plus, you have to distinguish boundary condition for the translation. So here it's a double minus. So it's clearly that the T to the plus 2L is equal to 1. On the other hand, minus sign, you get the minus sign. Okay, so that's what we have. Any question at this moment? Let's keep. So let's keep this operator into examine its just definition of T. And this is the central topic of this lecture. Okay. Yep. Now, so what's important of this one is that if you use this transformation rule, what we can do is h plus minus is equal to minus j to 1 and then L sigma j x minus sum over sigma j plus 1 and j to 1 then L minus 1. So important L minus 1 then the plus minus 1 to the sigma L sigma 1. Okay. Fine. So the important thing is that here now, since we impose the boundary condition and so on, and here we just need to introduce something non-local plus sign, and also here the last time I was sloppy about this issue about the global structure of this Hamiltonian. And here you need to impose minus 1 to the f, which is a product. Minus 1 to the f. Here is the product of j to the 1 to 2L plus L sigma j and then x. Here we need to impose this minus 1 to the f. So therefore here you just can see some non-locality. Non-locality because of minus 1 to the f. So important thing is that here last time I just exactly mentioned that Ising is equal to free Fermi. I didn't mention Majorana because I mean it's just assumed that it's real. But the last time Ising is Fermi, but there's a issue about And when you come back to the original side, then -1 to the f. And also you need to consider boundary condition. And 4 parameters. So therefore I just put the question mark. Last time I was very sloppy at this point. Okay. Okay. So now we consider something called, in fact, this is not equal. What we need is Ising is equal to Majorana fermion divided by f. In fact, this is true. So this divided by -1 f is called so-called the discrete gauge. You have to average over -1 to the f. You have to average this thing. To consider this divided by -1 to the f, but we are going to consider we consider so-called enlarged Hilbert space. So I can erase this part. Okay. So Hilbert space, enlarged Hilbert space, you just consider the direct sum enlarged Hilbert space as direct sum, which means the h, I call it tilde, is equal to h plus or h, I call it h minus h plus. So therefore this is 2 to the, so each Hilbert space have, as I mentioned, 2 to the l. But you have 2 copies of them, so therefore 2 alpha dimension. So this h tilde has a 2 to the l plus 1 dimensional. And on and capital H, and this is solid h tilde is a Hamiltonian which acts as diagonally on this Hilbert space, like this combined system. Okay. So that's the condition we consider in here. Okay, so that's the condition we consider. And now we just consider something called this mode by -1 to the f. So this is a discrete gauging we are going to consider. And then I think this part I already explained last time, so I think I can erase this part. Okay. And in fact, previously I used capital X, capital Xj for the power matrix, but this one can be understood as the, okay, let's talk about this one later. And now, so we will consider discrete gauging. So how does this -1 to the f is behave under translation? Let's consider this one. Okay. Let's consider how does the -1 to the f behave under conjugation of the translation. Okay, maybe inverses. Anyway, so that's awesome. So we know the definition of -1 to the f is this guy. Okay. Okay. Sorry. I think I told you wrong. Yeah, so sorry, this -1 to the f is this guy, so this is not true. Sorry, this is not true. Sorry. This is not true, so I told you wrong. So -1 to the f is this. Sorry. -1 to the f is here. Okay. what I'm doing there. Let's see. I think it's okay. Let me think. Just a moment. It should be okay. It's just compatible. It should be compatible. Because if psi is written like this, right? Psi to L is product of sigma x, L, whatever k equal to 1 to L, and then sigma, I don't remember y, L minus 1, and psi to L minus 1 is something the same piece, sigma z. I don't remember which one is which. I'm not good at memorizing things. What's the definition for me? Yeah, I think it's okay. Like this one. And if you just multiply them honestly together, you should get this way. Is equal to product of sigma x L. That's equal to 1. So that's fine. Now, yeah, it's compatible. So now, you just do the computation, and this is I to L, psi 1 to psi to L, T plus inverse, right? And then each time this T plus is translation. So this becomes psi 2, this becomes psi 3, and then this becomes psi whatever 2L, and this becomes psi 1, right? Right? And then we need to bring psi 1 to the here. Okay? But you have an odd number of this one, okay, in total. So therefore this one is equal to minus 1 to the okay. So you have a negative sign. On the other hand, T minus 1 to the F, T minus inverse is minus 1 to the F. Because of this boundary condition, there's a 1 minus sign is coming. Okay. So there's a difference between how this translation acts on the minus 1 to the F. Now, so that this mod means that we just project Hilbert space. The we are looking at is the total Hilbert space H tilde and projection by minus 1 to the F. So therefore, so therefore minus 1 to the F acts on plus 1 and minus 1 on Hilbert space of under periodic on minus 1. And we just project on the Hilbert space, total Hilbert space H tilde by this operator. So this is by projection. Namely, we just 1 plus minus 1 to F divided by 2 H tilde. So that's the Hilbert space we consider. Okay. That's the Hilbert space we consider. So that's the meaning of this minus 1 to the F mod. Okay. So this is a projection of by minus 1 to the F. Okay. Okay, now I think so the T tilde, did I write T tilde somewhere? Okay, T tilde here. T tilde here is the T minus T plus acts on this on the Hilbert space here. Does not act on H, which is H tilde projection. Because of this property. So the T plus is you get the minus sign here, whereas the T minus acts on the minus 1 to the F. Okay. It just T minus acts on this minus 1 to the F as it is, but on the other hand, the T plus acts on minus sign here. So this T plus is projected out on this on the projected Hilbert space we are considering. Okay. On the other hand, we have this T is equal to T tilde square, which is T minus square 0 0 T plus square. This is intact because minus T plus square, you get the minus square is equal to plus 1. Okay. So therefore, T, which is defined as a T tilde square, acts on this Hilbert space. Okay. So this acts on Hilbert space. Moreover, so this is exactly translation we consider in the Ising model. On the other hand, D, here T, we consider T tilde, but this does not act on H because T plus, you get the minus negative sign. So therefore, this projection operator, under this projection operator, the T plus is projected out, but T minus is innocent. Okay, you don't have a minus sign, so you can survive this. So D can be defined as an active factor, square root 2 factor, as T minus 0 0 0. It acts on H. Okay. Acts on H. And this D is exactly this guy. Exactly this guy. It becomes exactly this guy. Under the following condition. The following identification. So now you see why I use the capital X and capital Z metrics for Ising model, because so capital Xj can be identified for sigma Xj. On the other hand, Zj is sigma J. And then, so you just identify the capital X and the capital Z as this operator, or acting on this enlarged Hilbert space, and you just project it out on the this minus 1 to the F. You get the desired operator. You get the desired operator. And from there, actually D square. If you do the D square, what you get is that essentially 2 times T minus square 0 0 0. Okay. That's what you get. And this is exactly equal to 1 plus A is equal to T times T. T is given here. Okay. T is given here. But 1 plus 8 is the sign flip operator. Right? Sign flip operator. And that will project out of the this half of the Hilbert space. That's how you get the relation between D squared is equal to 1 plus 8 times T. Any question at this moment?
Minus 1 over T minus plus 1 on this
So you mean this one?
Yeah.
Let me think. So T minus is the T minus commute with Hamiltonian, right? Is equal to 0. And then Hamiltonian, so it's not. It's Hamiltonian, right? And then let me think. Let me think. I mean, it should come from this computational relation. Sorry, I don't have a good answer to this at this moment. I'll think about it. I don't have a good answer to it. Let me think. No, I don't. I cannot answer this. Okay, I'll let you know if I have a if I can answer the question. Okay. Anyway, so that's the so anyway, so the how you derive up to this minor point. How you derive d squared equals 1 plus 8 plus 1 plus 8, you just project out the half of that. So therefore, that's the non-invertibility. Non-invertibility. Coming from. Another way to derive this one is using so-called matrix project of matrix product operator. There where I use the D is equal to trace of U1, U2, U, L, such that the U is equal to 0 plus J, so J is equal to 1 minus J, 0 minus J, and 1 plus J, like this. Okay, so 0 is the okay. So the sigma z 0 is minus 1. 0. I mean it's 0 1 is the eigenvector for parametric sigma z. On the other hand, the plus means that the x vector is plus. And then minus is like this way. Eigenvector of the parameter is sigma. So therefore, plus is essentially 0 plus 1 divided by square root 2 or something. Something like that. and then plus minus is something. That's the definition. Okay. Now I erase this part. Okay. So this one can be just understood as there is something like tensor network. So you just assign each side, you assign the matrix U1, and then just multiply it in the horizontally U2, and so on. J equal to 1, J equal to 2, and then 3. Okay. And then you just trace like this way. This is schematic diagram for this operation. Okay. So it's from bottom to up is kind of like the time transition. So if you have only like this kind of transformation, it's just unitary operator. But now we have a horizontal line, and then just trace it, take a trace it. This means that it kind of like a non-unitary. This kind of stems from the fact that it's non-unitary. So U is a 2 by 2 matrix, 2 by 2 matrix, and then with different bases, and you can just multiply them together. So therefore, you can take a trace. But this is essentially just doing the horizontally like this. Okay. And then one can show the following. Maybe I can erase. Yes. If you do the brute force calculation for this matrix, one can just show that the brute force calculation, one can show this is coincide with this operator. Brute force calculation. But another way to derive this computation ratio here, or the dE is exactly this guy, is as follows. So if you just consider Uj, so it's 2 by 2 matrix and acts on Xj, and this one is exactly Z, U, J, Z, where Z is given by 1, 0, 0, minus 1. So as I mentioned, this is the U is 2 by 2 matrix, like this way. So therefore, if you define Z as like this way, you can define it. So this can be understood as the following. So this X acts on U1 is equal to Z. Sorry. Z, U, Z. I call it Z, just simply Z. Like this way. So locally, you can just write down like this as a diagram. So first you act on Xj as a site, and then next you apply the U. That's also you can do. Is equal to this one. Okay. And also one can show that the Z acts on U. Uj is equal to Zj is like this Uj. So this can be understood as the diagrammatically. This is Z acts on U from left is equal to like this. No, the opposite. So now it's a left. So therefore it acts on like this. Okay. So this operator X or this Z without this double notation, is a horizontal. It acts as horizontally on a side. Each side you just act on a side. Okay. Now, if you use this notation, you can show that what we want the Kramer-Swallow transformation is what we want is this one. So this is the Kramer-Swallow transformation we want to get. X goes to Zj times Zj plus 1. This one can be understood as follows. X is equal to, so here, the horizontal, D is this, you just multiply them together and they come back. So therefore, D can be understood as this horizontal line and then come back. But if you localize, so this is J side, and J plus 1 side, and so on, is equal to, you can apply this one to here. J plus 1, and then it's equal to, and then just next time you apply this rule. Then you have diagrammatically you can apply. So therefore D times xj, D times xj. So first you act on xj first, and next is D. Is equal to D times Z times D. So this is J side and J plus 1 side is given here. Okay. So that's exactly what we need. So this transformation rule can be derived, but you need a little bit work to show this relation. You need a little bit of work to show this. But diagrammatically, so you can just show this Kramer-Swallow transformation by a very simple way. Okay. Similarly, maybe I can erase here. So similarly, one can show that the following thing. So Zj times Uj is equal to Uj times something called x. I call it something x. And then x Uj x is very similar to Z over there. I'm not going to write down this. X is something very similar to 0, 1, 0. This is x. And is equal to, what was that? Sorry. Xj times Cuj. So that's that rule we can consider. So if you use this relation, so diagrammatically, this upper one can be understood as follows. Z acts is equal to U x like this one, diagrammatically, and then this one can be understood like this. Okay, so like this. So now, one can show that the D, then Zj plus 1 is equal to Xj plus 1 D. So this is another Kramer-Swallow, one of the Kramer-Swallow transformation. And this one can be diagrammatically understood as the Z and Z like this way. And then now we apply this rule, so that the okay, like this way, and then apply this rule, and this is equal to like this. Okay. So this is j plus 1. So therefore this is j plus 1. So this is diagrammatically to show this relation as a matrix product operator. So open people for NPO. So therefore this MPO, the way you define D will satisfy this desired property for Kramer-Finite transformation. Okay. Fortunately, I already erased Unfortunately, I already erased. So what we have is another relation is the A to D is equal to D A is equal to D, and then the other is D squared is equal to 1 plus A T, and another thing is the what D T inverse T is equal to D diamond. Okay, so that's another thing we can consider. So one can show this one very easily. One can show this one very easily. So recall that the eta can be understood as I to the L x1 dot xl. So that's the eta we define, the sign flip operator. So this can be understood as the following. So the D times eta times D is something like this one. Okay, like this one. Now how you apply which rule? This rule here. You apply this rule. Okay. If you apply this rule, instead of x, you have instead of x, you have a z here. Z. Everything z. And we know Dj squared is equal to 1. Dj squared equal to 1. Okay? So therefore, they cancel each other. Okay? And what's left is something like this one. D itself. Like this. D itself. So therefore, D times A is equal to D. And then you can do the similar thing for another thing. A times D is equal to D, you can use this one. A times D, you can use this diagrammatic approach for this one. Yeah, this one. So you can use this one to show. And so D squared is equal to 1 plus eta times T is a bit more complicated. So I'm not going to derive this one, but that can be used, can be shown by using this one. Okay. So that's the very, very brief introduction of the non-invertible symmetry for in Ising model. So D is the actually non-invertible symmetry which generated Kramer-Swammer transformation at the Ising CFT, but it's not the invertible. So that's the okay, and then they satisfy some algebra. Okay, let's stop the here. And then take a break. And if you have a question, just let me know. Okay. Shall we resume? Is it okay? Things are not. Okay, let's wait a few more minutes. Like it. Okay, then let's get resume. So your question, minus 1 to the f is plus 1 on h minus, what is minus 1 on h plus? So this is coming from this, if you do the Jordan-Wigner transformation like this way for psi, you write down Hamiltonian, which is something like what? Sum of psi L, what? Plus 1. I hope it's okay. Sorry, I think it's something strange. So L and L plus 1 is here. Sorry, L plus 1 is not 1 to the L minus 1, and then I multiply I. Yeah, I. And the bottom plus minus, and I sine. Oh, yeah, it's okay. And plus 1 is here. And 1 and sine to that. Okay. So if you use the Jordan-Wigner transform, you get this one. So at the end, you get the minus 1 to that. So therefore, with this choice of Hilbert space of under period plus 1, you get plus 1, and the other period is minus. So therefore, it aligns with the Ising Hamiltonian. Okay, so everything needs to be negative sign. On the other hand, if you pick minus 1 to the 1 on the periodic Hilbert space, this is minus 1, and times plus, you get a minus 1. So therefore, it aligns with Ising. That's why we pick this choice. Okay, so that's the answer to your question. Okay, so that's the thing I wanted to explain, and then yeah, I mean, so this D plus, so we can do the following. I mean, D plus is something like it's very similar to. So it's very similar to this one. So the dagger. So sorry, it's not D plus. The dagger is trace of something like a U tilde 1 U tilde L, and it's just it's almost like a same transpose of this one. U tilde J is something like plus 0 J, and then minus 0 J, and minus 1 J, and then plus and 1 J. So this is the U tilde. If you use this one, you get the dagger. Yes, and then moreover, U tilde is related by HU, where the H can be written as square root 2, 1, 1, 1, like this. So one can just write down. Okay. This way we can do the computation. Fine. Okay. So what's nice about this D? So non-invertible symmetry is that so you can say something about the Hilbert space on this Hilbert space on the system, physical system. Where did I? Okay. So then. So we can deform the system that the so Ising Hamiltonian is as again given by like this way G times xj minus G inverse sum of the j Cj plus 1 you can deform like this. Okay. So this was original Ising Hamiltonian. So one can deform this one, okay, by following the term. But this one is the preserved D. So recall that the D acts on xj is gj plus 1 D, right? So if you act on D on x, you get this term. On the other hand, if you act on D, j and then D, j plus 1, you get the xj and D. Okay? So therefore, if you act on this term, you get this term. Okay, this term, next form. So therefore, this term preserves D. That's why you choose this one. So this is the linear, and this is quadratic in polymetrics. This is cubic. Okay, cubic in Hamiltonian. But you just have a deformation parameter lambda. That we can. So when G equal to not 1, you have a symmetry operator, but D does not exist. So D is the Kramers-Wiener transformation that only exists in the G equal to 1, because I mean it's just going from. Otherwise, you just go from low temperature to high temperature, low temperature. So it's not the symmetry of. If G is not equal to 1, there is no D as a symmetry. But lambda, if you turn on lambda, A and D both exist. Okay. So sign flip does not. Sign flip and D commit with H. Once you set G equal to 1, of course G equal to 1 is asymmetry. G equal to 1 is asymmetry. It has a both symmetry. Okay. And the question is what's going to happen in the system. So now we just write down phase diagram. So if you condensed matter balances, we always write down phase diagram of this Hamiltonian. So this is G, and G is a lambda, and this is G equal to 1. So then mention. So this is the disorder. This is order. You can say, let's say this is G. And then here we have a ground state, so E, and then you have a ground state 1 equal to 1 or 0 equal to 1. So degenerate. Ground state as degenerate. On the other hand, and then it's gapped for 1. So the first excited state is the has a gapped. Okay. The same thing as here. So E is here, but the ground state is just a disordered one. So plus is the eigenvalue of the eigenvector for sigma x. Okay, sigma x. And then the ground state is plus 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 plus. And it's the first excited state is the order 1, it's gapped. On the other hand, the last time what we saw is the Ising CFT. Here you have the spectrum is this gap is the only 1 over L. And if you take the continuum limit, it becomes gapless. Okay. That's what we saw last time. By just doing the Jordan-Wigner transformation and just write down Hamiltonian by the like this way, and then just diagonalize. And then we saw that this spectrum of the theory is the related by, I mean more precisely Finch, something like I don't remember, the K over L to pi or something like that. The spectrum is where K is some round for 0 to L minus 1 or something. Anyway, so that's how the spectrum looks like. But in any case, it's just order 1 over L is the spectrum. And then once you take L with the infinity limit, you get the gapless. Okay, so that's what's really happening in the Ising CFT, where lambda is equal to this one, and then this one in this order space. This is the order. Fine. So once you turn lambda, in fact, this is called irrelevant deformation. Irrelevant deformation. I will explain it in coming 2 lectures. What's the irrelevant deformation? Irrelevant deformation is that if you just turn on this irrelevant means that literally this deformation is irrelevant. So therefore, even if you turn on this lambda, it's still Ising CFT. And at some point, you get something called tricritical eigenmodel. So at some point, tricritical eigenmodel, some non-perturbable factors become important where C is several. And then after that, it becomes this part. It's gap. So gap means the energy is here, and the first excited state is the kind of like a really discrete spectrum. But at ground state, you have a 3 degeneracy. So the state is, as you can easily guess, so at the disordered state, you will get plus plus plus, and then for all the states, the ground state 1 1 1 or 0 0 0. And if you look at the here, it becomes the ground state is something like okay. These 3 states. That's the yes, shortly. So this, yeah. So here I think track regard this is gapless. But if you just turn on lambda, it becomes gapped. And in particular, so you just set g equal to 1, and then equal lambda equal to 1, and this Hamiltonian can be written as follows: 1 minus xj minus 1 j like this. you can write down a very simple way, and you can show that the both you can show that this plus 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 0 0 0 and 1 1 1 has the same eigen same energy. You can show this. You can show this. I mean, the plus 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 is just an eigen vector of x, and 0 0 0 1 1 1 is eigenvector z. So you just add this h on this one and compute the energy. Okay? And you can show that they have the same energy spectrum. So you can just directly compute in this one. And also, since we know the definition of d is something like, I don't remember, something like 1 plus ix square root 2, 1 plus I z j plus 1 square root 2 j, and the last one is the and then 1 plus I xl square root 2, and then 1 plus a over 2, and so on, and some prefactor here, which is also important. And if d acts on this acts on this ground state, you will see the following thing. So you will see that the d acts on plus plus. You get 0 0 plus 1 1. That's what you get. On the other hand, d acts on 0 0 is equal to d acts on 1 1, and which is plus. Okay, like this way. Okay. On the other hand, so it's a nature of non-invertibleness. So if you act as the d acts on 0 minus 1, this will equal to 0. Okay, so this state is projected out. Okay, projected out, because that's very natural. That because I mean here is under eta it's spin odd, right? Under eta it's d2 odd. It's just spin flip symmetry. This is odd, so therefore it's projected out because of this way. Because of this. So that's the how this d acts on the ground states. So therefore, I mean, the non-invertible symmetry somehow always has a kernel. Okay, has a kernel because it's non-invertible. Fine. So that's how we can see d acts on the ground state and so on. Okay. So that's I just wanted to explain the non-invertible symmetry in the Ising model. So this is a very hot topic, and I think even that once we learn this Jordan-Wigner transformation, one can just understand what the non-invertible symmetry is. Jordan-Wigner transformation is Kramer's-Wiener transformation. This non-invertible symmetry naturally appear into this area. Any questions? If not, I will move on to Conformal block. That was the original plan. Sorry. So I just want to detour. It's okay. I mean, it's sometimes it's good to see some close to research topic. It's good to deal with some recent development, even in a class. Any question at this moment? Okay, if not, I will move on to the. to move on to conformal. Okay. Last time I briefly talked about conformal block, but it was very schematic. So let's do it very carefully. Okay. So if you consider correlation function, so correlation function of this 4-point function. No. Like this way. We consider correlation function and take the okay. You just consider 4-point function, but we can set the following thing. So z1 to be 1. So z1 to be 1. So sorry, z2 to be 1. And then here you can have a cross ratio x and x bar. Cross ratio you already knew from the homework, and then 0, 0. You can set like this way, and the multiply, I don't have a space, so therefore I just put that here. Z to the 1 to the 2h, z1 bar to the 2h bar, and then take limit z1 and z1 bar goes to infinity. Z1 bar goes to infinity, and then call it this one z equal to g 2, 1, 3, 4 x and x bar. And call it this one like this. And this one can be written, so this one can be written as follows. This one can be written sum over C1 2P, C3 4P, 2, 1, 3, 4, Px f bar, 2, 1, 3, 4, P and x bar. And then our P is something like this one. P is the P is primary field. Primary field. Primary is that's how we can write it down. And then so the last time I somehow omit the other homework part, but if you restore other homework part, it becomes like this one. And this is called conformal. And this one can be obtained as follows. How? So this one, so this conformal block 2, 1, 3, 4, P and X can be obtained as follows: HP minus H3 minus H4, and the sum over lambda. Lambda is a partition, and then X to the lambda. Okay. And then here we have the following sum. How can I? Okay, lambda and lambda prime, P and P. What's that? Oh no, P is, we don't need P. So this one can be written as follows. So the H1, okay, maybe I need to write down, okay. H1, phi 2, 1, and then lambda minus lambda, L minus lambda HP, and HP, and then here we have the following HP, and then L lambda prime, and lambda prime phi 3, 1, and H4. Okay, and then divided by appropriately, divided by it just normalized like this way, and then here you have lambda and lambda prime. I think this lambda and lambda prime, the number of box should be the same. And then you have HP by 3, 1, and H4, which is appropriate normalized. Then you have the inverse of Shapov-Balogh matrix times G P HP lambda and then lambda prime and inverse. So that's the component you get. Okay, so that's the schematically. So this is as follows. You have a phi 1 at the infinity and phi 2 at the 1, and you have here you have a phi p lambda. You have a phi p lambda. Phi p is the what was that? This one is defined as L minus lambda 1. Sorry. It should be okay. Dot 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 minus lambda 2 dot 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 L minus lambda L acts on phi p. Phi p is a primary field and L acts on it. So this is descendant. Is this one? And then times. So you have schematically. So that one. So this part is this one. And then, so this part is the phi 3 x and a phi 4 0. I mean here x, instead of x you have a y here, but that because we put all the x dependency out of the computation. And then here you have a phi p and lambda prime. You have a phi p lambda prime. So you have a different descendant. You have lambda prime. So it's a different phi p lambda prime, and this is the different sequence lambda prime L minus lambda prime whatever m phi p. But important thing is that unless the number box, so as I mentioned, lambda is the Young table or partition, whatever you call it. And the number box lambda is sum over lambda I don't know what essentially, so you just count number of boxes of Young table like this way. Anyway, lambda 1, lambda 2, and so on. Lambda 3, and so on. And that's what you did. And number box has to be equal. Lambda and lambda prime has to be equal. But then when they group them together, you just multiply by Katz-Shapov-Balogh matrix inverse. So that's a schematic figure of this conformal block computation. So this part corresponding to this part. Okay. And then when they glue them together, you just multiply by this inverse of Katz-Shapovalov matrix, Katz matrix. Okay. Okay. You just multiply this one. So the Katz-Shapovalov I already explained many times, right? So, minimum model, you compute it anyway. So let's recall this lambda and lambda prime is just a HP, and then L lambda, and then L lambda prime and HP. So that's the element of the Katz-Shapovalov matrix. And then when lambda number box on lambda prime is the same, this is non-trivial. It will give you a non-trivial element. And fine. Okay, so now how you compute? We know that how you compute Katz-Shapovalov, and the question is how to compute the three-point function with descendant. So that's a question to how to compute the Katz-Shapovalov matrix. But that's also difficult. In fact, let's see. So let's consider the following thing. So let's consider. So let's look at this one first, and compute this one. 5p minus lambda prime. Like this way. So now we just try to compute this one recursively. So let's consider lambda prime is something like this one. Whatever. So this is lambda prime, and we just put the, in addition to that, we just put basically, yeah. So we just put like this way. And the boxes. Something. And the boxes. So this guy is, this white one is the lambda prime. And in addition, then you just put the n boxes like this way. Okay. Okay. So then, so we know that, so here, whatever. 5p is something like 5p is at the infinity. At the infinity, and then 0 is 5.4, and 1 is 5.3. Okay, and then we just do the contour integral of the infinity of this one. But that is equivalent to the just deforming something like this way. Yeah, that is equivalent to deforming like this way. Okay, and then you have to be careful about the contour that you will take. I think there's something strange about sign of this integral. Which one is correct and which one? I don't remember. Anyway, so the up to psi is okay. Let me think. So T of Z is again Ln over Z n plus 1, n plus 2, sum over this one. So to get the L to the n action on here, to the left, we just need to multiply Z to the n plus 1 and pick Ln. Z to n plus 1 cancels Z to n plus 1, you get the 1 over 0. And if you just integrate over the infinity, you get the ln action on the infinity. And you have to be careful about how you do the integration. I think most likely the proper integration of the infinity is opposite. That's most likely. So you have to do like this to get the correct integration on the infinity. Okay, and then do this integration. So do this integration. So you just split this one into two parts of the integration. So one is around 1, one is around 0. So you just split it into two integrals. So 2 integral. So then, fine. Then what you get is the integral of C0 dz 2 by I. That acts on okay. So now, so if you just only look at the 0 here, so the stress energy tensor T acts on the operator of 0. So energy T acts on operator 0. So therefore, like this, K is integer. On the other hand, if you look at the integration on the 1, and then what you get is that the okay, like this. So now the stress energy tensor T is not expanded around the z equals 0. Now it's expanded around the z equal to 1. Okay. So this is the expansion where k is integer. And do the computation. And then nobody, okay, anyway, so do the computation. And then here, this part we need to expand. This part we need to expand in terms of z minus 1. And in fact, this one is equal to sum over L is equal to 0. It's just I don't know, what is it called, binomial theorem? Choose L. Binomial theorem and z minus 1. Like this one. Okay, by binomial theorem. And then plug that into here. And what you get is as follows. So this one is equal to 5p minus L prime, 531. And then ln 54 and 0 plus Okay, like this. So you just plug this one into here, and you pick only one of the z terms, so therefore you only see the when k equal to n. On the other hand, here we have the this expansion, so we have this second term. We have this one. But on the other hand, that we have to recall that so those phi 3 and phi 4 are primary field. The primary field, the differential primary field is the phi prime p is equal to 0 when n is greater than 0. That's the definition for primary field. And phi 3 and phi 4 primary field. So therefore, only n, when n is non-positive integer, you can just have a non-vanishing term. This is also same. You can have L minus 1 is what was that? Non-negative. If it's non-positive, if it's not positive, one can have non-trivial term. So that's the how it works. Okay. So let's suppose that L here is the okay. But here we assume that here is we assume n is greater than equal to 0. Okay, otherwise, this is also vanishing. Therefore, what we solve is that as follows. So what we solve is that so this one is equal to first of all, when only n equal to 0 will give a non-trivial term. So therefore, delta n 0, and if you L equal to 0, it just gives you a conformal weight, conformal dimension for H4, and then we have something like gamma prime. And suppose when L equal to 1 case, this will give you the again conformal dimension for H3, for phi 3. When L equal to 1, this will pick n plus 1 and H3, and then the same piece. We have this piece. And then another non-trivial one is when L equal to 0. When L equal to 0, what you get is the okay, so that's what you get for L equal to 0. Like this one. Fine. Okay. But now, so you recall this one. So if you look at this one, so you can just recall the phi 3. And then Z and phi 40 is something operator product expansion. What you get is Z to the H3 plus H4 and divided by minus HP minus lambda. And then here you have a phi P and then minus lambda P and lambda. So that's operator product expansion for primary field. Okay, for primary here, okay, like this way. So therefore, and L minus 1 is just a derivative. So if you act L minus 1 is equivalent to the L minus 1 acts on it is the same as Z derivative acts on it. Okay? So Z derivative acts on it. Okay? Because of the conformal word identity, conformal word identity. So therefore, if you have the derivative, you pick only this one. Okay? This one. So therefore, so that this term is in fact equal to HP plus lambda prime minus H3 minus H4, and the same piece. You just have some derivative of this term on Z, and take Z equal to 1 limit, and you get this one. You get this. So just summarize this one. What you get is at the end of the day, what you get is that this one. So at the end of the day, so you will get at the end of the day, this one is equal to so H4, and then this block. Like this. Okay, like this. Okay, so this is essentially the effect of adding this. So important thing is what we did is that starting from here, you further act on L minus n. So this action on here will just cause this number. Okay, that's what it means. That's why you have a dependence on n here, and it depends on all the conformal dimension and L prime here. Okay. Any question at this moment? And you can do it recursively. So this means that it's a dimension. So you just have a lambda. You have lambda, whatever. Lambda. So this is lambda prime, and you just add the n boxes here, n boxes here, n boxes here. That's the cost of this one. So therefore, you can just do the recursively like this way. You can just have a recursive relation. But therefore, this conformal block. Now, three-point function with the primary descendant is just 5p minus lambda prime 531 540. It's just a product of L lambda prime I equal to 1 HP plus lambda I prime H3 minus H4 plus like this one. And then seems like I made a mistake in sign in summer. Yeah, I think this should be minus sign. Most likely this should be minus sign. Am I correct? Let's see. So here minus sign, right? And when any, so we assume n is not 0, so n equal to not 0, this will go, right? So it should be minus sign. On the other hand, this minus H3 cancel with this n plus minus H3. So you get the plus and H. It should be okay. So this should be okay. Okay, so that's the answer you will get from this analysis. And then same analysis can be done for this one. For the other, unfortunately I'm too stupid, I erased this part. For the other piece is something like this one. For the other piece is phi 1 infinity, phi 2 1, and phi p and minus lambda. So that's what we saw for the other pieces. For this one, to hold this one is equal to product. It's same analysis we need to do. HP lambda I H2 minus H1 plus product of Hj, J is greater than I, and like this. Then I is equal to 1 to L lambda. Oh, by the way, L is the length of Young tower. This is L lambda. Or whatever. So that's the another piece of to compute the conformal block. Okay. Then we just need to combine them together, glue them together by inverse of Katz matrix. Inverse of Katz matrix, and you can compute by order the conformal block. Okay. So that's not so difficult. I mean, does it? No, nobody have this adapter that connect this one to MacBook. Does anybody have this connector? If you have, I can show mathematical computation to do this kind. I mean, if you ask a mathematical, it's easy to do the computation order by order. This kind of computation. Nobody. Okay, maybe next time. Then I will show by how to do the computation and so on. So yeah, as I mentioned, so this one, so this is one piece and another piece, and I can erase this part. Okay. So as I mentioned, so this one, so phi 1 infinity, phi 2 1, and then phi 3x, and phi 4 0, and then here phi p minus lambda prime, phi p lambda minus lambda, and then you just join them together by lambda and lambda prime. So that's how we compute conformal block. So that's how we compute. So we know that each piece is how you compute. We know G how to compute the Katz-Shapiro matrix. So this one corresponding to this guy, and then this guy corresponding to this guy. So everything in terms of what we did is all the manipulation here is just computation ratio of the Virasoro algebra or stress energy tensor, the OP with stress energy. Okay. And then this will give you a control block. So that one, F2134 PX. Okay. One of 10. And then the important thing is that the so-called crossing symmetry. Crossing symmetry. So that is schematically shown 1, 2p, 3, 4p. Okay. Oh my goodness, I'm something too okay. And phi 1, infinity, phi 2, 1, phi 3, x, phi 4, and 0, and phi 1, infinity, phi 2. So like this. So this is the cross symmetry. What I mean, like this. Yeah, here in the middle you have assumed this as conform family of T and conform family of Q. And then to move the position of phi 1 and phi 2, you need to just change the cross ratio. So change. So here phi 4 is at the origin, whereas the phi 2 is at the 1. Then it's opposite here. So to exchange this one, you have to change the cross ratio. And yeah, so this is essentially f1, 3, 4, p, x. And that will give you f4, 1, 2, 3, 3, 2, 3, 2, q, 1, -1. And of course, you have to consider anti-home part appropriately. That's the crossing relation. So the computation is totally different. So computation is totally different, but they should agree. They should agree. Okay. But in the case of Virasoro, it's a Virasoro, or 2D CFT, Virasoro algebra is so powerful that the conformal block can be just computed by hand, like this way, times the cut matrix inverse. But in the case of the high-dimensional conformal field theory, things are not so simple because of you don't have a Virasoro algebra. So therefore, to compute conformal block, one has to start with this identity, crossing symmetry, to compute the conformal block. So that's it's called the idea of conformal bootstrap. So using this crossing symmetry, so it's just an orientation reverse side. In 2D CFT, you can check that you can compute this one, and you can compute this one by using Virasoro algebra, computational relation Virasoro algebra. Then one can check this will hold. For instance, in the rational conformal field theory, a minimum model. But for higher dimension, crossing symmetry determine conformal block. That's the rough idea of conformal bootstrap. Okay, so that's the I wanted to explain for conformal block. I can show you something. Now I kind of think about it. It's better to talk about the It's better to talk about the homogeneous invariant partition function or torus partition function. But let me think about it. Okay. So one thing one can just show is that so different bases for conformal block will give you different. So this one I. Sorry, JK. I mean here it's just schematic, and then P. It's something like a different basis of conformal block, P and Q. Because fusing, the order of fusing is kind of doesn't matter to compute conformal block. and J and L, okay, or sum over Q. Okay, so this is the different basis for conformal blocks. So that I change the fusing of IJ first fusing, it's called fusing, or like taking OB first for I and J, and you get a P, and then K and L. So or I and K, you have a fuse, and you get the Q and J and L. So you have a different basis of conformal block. They are related to so-called braiding matrix. Another one is this something like this one. J, K, I, P, L, and is equal to sum over F, P2, J, K, I, L, and this is the Q, sum over Q. And this one is called, F coming from fusion matrix. Sometimes many names, so 6-J symbol by Wigner, or sometimes Raka Wigner. Matrix. So different bases, you need a base change from different bases of conformal block. That will give you that you need to do a base change transformation. That is called braiding matrix and fusion matrix, and they satisfy the following thing. It's called pentagon relation. I don't think I have a time. Okay, it just give you some constraint. I don't think I have a time to talk about everything. So you start with this kind of conformal block, I, K. Okay, maybe start with here. I, J, K, L, M. And the braiding matrix would tell you I, K, J, L, M. And this one is the same as the Yang-Maxwell equation. J, M, and I is just mark 2. I, L, K, J, M, I, like this one. So you just swap first J and K first, and next to J and L next, and L and K, like this. On the other hand, you can do the opposite order. So first K and L, K and J is marked to and like this one. So this is called a pentagon relation, hexagon, hexagon relation, hexagon. So this gives you something BBB is equal to BBB. So each transformation requires a braiding matrix. Okay, so this is called hexagon relation. On the other hand, for fusion matrix, you need a pentagon relation. Essentially, what you get is FF is equal to FFFF. So that's the pentagon relation you need. So those are the constraints coming from the how you transform the conformal block. But so those are will constitute so-called fusion category and so on. So that I will briefly review the beginning of the next lecture, and let's stop here.